Okay, so yesterday we looked at how gases change, but we just looked at when two variables change and one variable remains constant. We are going to combine those three laws that we learned into the combined gas law. Unique name for it, huh? We're combining the gas laws. Because often they change, all three variables will change, so we need to be able to calculate them all. So what we use is, since it's pressure times volume, and then it was pressure divided by temperature and volume divided by temperature, we take the pressure times volume and divide all of it by temperature. Now we can use this if we want to say like the temperature remains constant. That means that T1 is equal to T2, right? So we could say P1 V1 over T1 is equal to P2 V2 over T1, because they're equal to each other. Now if I multiply by T1, what happens? They cancel out. So we can basically, whichever variable remains constant, we can take it out. And you're left with Boyle's law. P1 V1 equals P2 V2. If, let's say, instead pressure remained constant, we'd have P1 V1 over T1 equals P1 V2 over T2. So P1 would cancel out, and we'd be left with Charles' law. V1 over T1 equals V2 over T2. So it really, you only have to learn this one law, and it will break down into other ones if one of the variables remains constant. Okay, so let's try a couple problems, and then we'll get on to liquid nitrogen. So a helium-filled balloon has a volume of 50 liters at 25 degrees Celsius and 1.08 ATM. What volume will it have at 0.885 ATM and 10 degrees Celsius? So it's P1.
1.08.
What's V1? Liters, right? Over T1? Equals with P1? All right, it's in ATM, so that's what we need. V1 or V2? We don't know. T2? Everything's based on Kelvin temperature. Gas laws. Because the kinetic energy is related to Kelvin temperature, not Celsius.
Who is Kelvin? Lord Kelvin from Switzerland. No.
I don't know for sure.
It was in a book. I read it. I read it in a book.
Okay, so what do you get for V2?
Lord Kelvin. Why not just call it Lord Kelvin?
What did you get for V2? And what's our units? Liters. Good. 57.95 liters. Okay, the next one. What pressure is required to reduce 60 milliliters of gas at standard conditions at 10 milliliters at temperature of 25 degrees Celsius? What's initial, or P1? Yeah, we do. 1 ATM. Why 1 ATM?
Standard.
It's standard conditions, which means it's 1 ATM And what's the temperature? 0 degrees Celsius or 273 Kelvin. And what's V1? 60 milliliters. Okay. And that equals, what's P2? I don't think we know that, do we? What's V2? And T2?
Is 273 Kelvin standard?
Yeah. 298. 25 degrees Celsius is about room temperature. That's why we see it a lot here. So it's P2. Atmospheres. 6.55. Whoa. So that's a really high pressure. If you think of standard pressure at sea level is 1 atm, and this is 6 atm, 6.5, so it's 6.5 times the pressure. Okay, and last one, a small bubble rises from the bottom of a lake where the temperature and pressure are 8 degrees Celsius and 6.4 atm. To the water surface where the temperature is 25 degrees Celsius and the pressure is 1 atm. Calculate the final volume in milliliters if if its initial volume is 2.1 milliliters. So what's P1? And V1? We have 2.1. T1? Now P2. We're looking for V2 and T2. Yep. So what does V2 equal? $15.25? 14.25 milliliters. Yep, good.
So that's why when they tell you you're escaping from a submarine to always breathe out so that your lungs don't expand.
Probably, yep.
I watched that show.
Why would you escape from a submarine if you're underwater?
If it's
Sinking, like, or